Thank you for joining us. I'm excited to have John Duchi from Berkeley joining us today for the lecture. John got his PhD at Stanford, and then he had an actual job working at Google. Some of us might not be familiar with that, but he decided to move on to his PhD at Berkeley, where he's been working with Mike Jordan and Martin Wainwright. His work has had tremendous impact both in industry and in academia, and I'm excited to learn more about that. He's gotten a Best Paper Award at ICML. He's gotten some exciting fellowships, and he's done some of the most interesting work these days on large-scale and parallel and distributed machine learning. So we'll learn more about that today.
Okay, awesome. Thanks, Carlos. I'm really excited to be here, so thanks for the invitation. I know you guys are kind of far away and up the hill, but please stop me if you have questions. This can be interactive as much as you guys would like it to be, so don't hold back. Anyway, let's jump in. I'd like to start by enumerating what I see as some challenges in statistical learning and problems. So the scale of problems we're seeing is getting much, much larger. So in the first 2 months of its existence, the Sloan Digital Sky Survey had collected more data than the sum of all astronomical experiments to that point. We're getting image databases of hundreds of gigabytes or larger. Even The Economist knows that we're getting too much data. I mean, we're creating more information, more data now than we can actually store. So we have to throw away data before we even see it or do anything with it. We're getting new types of data, things like social networks. So this is a graph of dating relationships in a high school over a span of 18 months. And I really like, there's this one, the blue dots are men, pink dots are women. So there's this one dot sort of in that little cluster that you guys can see, that little blue guy. That guy is clearly not a statistician or computer scientist, but he had a busy 18 months. We're seeing really sparse data, things from like text data and things like that, where there's loads and loads of sort of zero features, things like this. There are computational issues we're facing. So we might imagine we have some kind of high-dimensional signal, and we'd like to represent this in some, say, low-dimensional basis. Nominally, this is a discrete or hard problem, but oftentimes, at least with the right types of data, we can relax these things into convex problems, or sometimes we can relax them further into smooth problems and still solve them accurately. So there are questions of when we can do this. We have issues of privacy now, of interaction with participants because of the data we're actually collecting. So in 2008, Nils Homer and colleagues took genome-wide association studies and showed that just by computing sort of marginal counts, counting how much variation there was on individual genes, they could actually go back and figure out participants in a study. And this caused the NIH to stop releasing data for a couple of months, and since then it's been very, very restricted. So these issues of privacy are actually, they're becoming real as we collect these new types of data. So what I want to try to do in this talk is develop a framework where we take some steps toward developing a framework where we treat all of these issues as constraints on the algorithms we develop and the inferences we make and our inferential procedures. So to me, fundamentally, sort of the exciting thing that's happening now is we're doing all these computations with loads and loads of uncertainty. And it's clear that statistical learning problems, we have these, but we're collecting data from crowdsourcing, and we want to do private computations, so we actually add noise ourselves, make the computations uncertain so that no one can figure out what we're doing. Databases, some people in this room have worked on like probabilistic databases, things like this. Networks, we don't know what the traffic's going to be ahead of time. So there's all these issues of uncertainty that we're facing now. But this leads, and my claim is that the connections between computing and optimization in the face of this type of sort of statistical uncertainty are incomplete. There's a lot of trade-offs here that we haven't really explored. And so the questions are, with this uncertainty, with this noise, how should we be doing our computations? How can we actually sort of leverage all the resources we have available and trade off between them? So I think, so in 2006, Jeanette Wing from Carnegie Mellon wrote an article sort of defining what she called computational thinking, where computer scientists, we maybe ask, what is computable? What's the best way to solve it? But there's all these problems with uncertainty now that sort of change the game. We have prediction problems, ranking problems, doing diagnostics, controlling systems, and these all sort of, maybe we don't actually care about computing things accurately. There's all sorts of questions here. But in all of these problems, I claim that there's essentially one sort of unifying theme, which I'll call risk. We have some loss that we care about, some performance metric that we care about making small, and we want to sort of estimate something that makes that risk, that expected loss, small. And we want to understand what trade-offs we have here. So now instead of just looking at the input size to our procedures and sort of the computations that we have to do, there's another axis that we want to consider things on. And we want to understand trade-offs amongst, say, all three axes or multiple performance measures. So we care about risk now. We want to see exactly what the trade-offs are here. And, or maybe we care about communication as a resource or privacy as some kind of resource that we want to understand what happens when we have lots of axes to consider. So I think this leads to a new type of thinking that is going to be really exciting, which is essentially statistical plus computational thinking. So in the face of uncertainty, how do we best trade among all the resources we have available and the statistical risk? All right, so in this talk, I'm going to go through resource constraints, or constraints on my estimation procedures at 3 different scales, sort of scaling up from local settings of looking at computational constraints, and then getting bigger, trying to understand communication between, say, processors or things like that, and then getting even further away from sort of these local scales and trying to understand interactions with people as a resource and viewing this as a constraint. So there's going to be one mathematical principle underlying everything I do in this talk, and it's called the Minimax principle. So the central object of study that we have is going to be what I call the risk. And so formally what this means, and I wish this pointer worked, but it doesn't show up. So we have some loss, which I call L, and the loss is going to measure, we have data X, and the loss and a parameter theta. And the loss is going to measure the performance of our parameter for individual data. And we try to understand what our expected loss is. So in a prediction problem, this might be the squared error we make in our prediction. So we have some X, and we try to make theta times X as close as possible to Y. So the picture here is, we have some data from some distribution in this cloud of pairs of X and Y. We get a pair. We try to make a prediction by computing theta times X. And the farther away we are from Y, the more loss we suffer. All right, and then we have some set of models that we can do inference or learning over. Say, for these regression problems, I have some data set. I want to fit a line to it. My parameter is just the slope of this line, so this might be all of the real numbers. Or in higher dimensions, r to the d. And we have some family of distributions that we're getting data from. So this is, say, data x in some box, say 0, 1, or 0, 1 in d dimensions. All right. So we have our risk, and this is what we want to make small. And so the Minimax principle, which in statistics came out of work by Abraham Wald in the 30s, and in kind of computer science, economics, game theory, work by John von Neumann in the late 20s, says that we want to choose the procedure, and I denote procedures by theta hat, which minimizes the worst case risk. So we have our family of distributions P that we might be getting data from that we can't identify, and we evaluate just our expected risk over that family of distributions, and that's how we're going to choose our algorithms to minimize this worst case risk. So it's basically a game between us, the designers of our procedures, and nature, where we choose our learning algorithm called theta hat, and nature chooses a distribution. Then we actually get to observe data from this distribution and make a decision. And that's what theta hat does. So that's our game. We try to make this as small as possible. Nature tries to make it as large as possible. But we actually get to see data. And then this principle has led to sort of tons of insights in computer science, statistics, optimization principles, economics, lots of places. All right. So this is, there's basically one formula for this entire talk that's going to govern everything we do. And it's almost this. We're going to make a tiny little tweak to this. So this is what's called the minimax excess risk. So what we look at is the gap between what our algorithm does. So that's this term on the left-hand side of the brackets. That's just the expected performance of our algorithm. And we look at how far that is from the best we could possibly do if we knew the truth, if we knew the distribution of our data. So we're just going to, this whole thing, we look at this the worst case over these distributions, best possible procedure. We try to understand how this gap performs. And I'm going to make essentially a 2-character tweak to this that's going to do everything for this talk. And that's the following. So I go from the minimum over all possible procedures to the minimum over procedures that belong to some class, which I'll call script C. And this class represents some kind of constraint I have on my procedures, some constraint on the resources available to it. So these constraints might be things like, say, procedures that do low computation or avoid communication or are actually private, meaning the data they release can't be backsolved for who belong to the data set. All right. So any questions on this, this one formula that's going to do everything for us? All right, good. Everybody's on board? All right, so let's just jump in, and we'll see what happens. So, oh, I'm sorry. I always forget I put this in. So basically what I'm going to try to do in this talk is take these kind of computing types of concerns, like computation, communication, and privacy, and this minimax framework for analyzing risk, and just add them together, and we're going to see what happens. So this is what we're going to do for this whole talk. All right, so jumping in, let's look at our first constraint. So we're going to start with a computational constraint and view it through the lens of optimization. So I said, we have some loss some risk that we care about making small. So nominally, this might mean I have to solve some kind of optimization problem. So I'm going to identify computation with optimization complexity. I'm not the first person to do this. Probably Nemirovsky and Yudin in the late 70s were the first to really dig into this. And then other people have built on their work since then, certainly. And the question is, how much optimization do we require to obtain an estimator with small risk? And we'll see 3 examples where this principle actually leads to nice practical algorithms that have made a difference. One will be in text classification, one will be ranking images, and then another will be in speech recognition experiment or application. OK, so let's write down what we're going to do. So we have some d-dimensional parameter theta. So this is the parameter we want to infer or estimate. And we want to find it by minimizing this risk, which is our expected loss, just our expected performance measure. And I'm going to assume that this loss is convex, meaning it looks like a bowl. OK, and when I said computation is optimization complexity, what this means is I have a black box, or a white box in this case. And in comes a pair x theta. So I get one observation from my distribution, and I can choose some parameters. They go in, and out I get an evaluation of my loss and a gradient of my loss. I'm doing optimization, so sort of gradients and function values are reasonable. So this will be my unit of computation. And then how do we set this up in the framework I said? Well, we're going to look at our minimax risk with n computations. So this is exactly what I said we do, except now my constrained class, my procedures, have to use at most n computations. And we want to understand how well they do. All right. So if we have a problem like this, some kind of optimization problem, a natural, say, first idea might be to use something like a gradient method. All right, so we have some risk. In this case, let's just say we have a collection of n observations, and we're going to minimize our average loss over those n observations. Our first strategy might just be to say, OK, we have a bowl-shaped function. Let's just go downhill. OK, so I take my current parameters, which I'll denote by theta I. I compute the gradient of my risk at my current parameters, and I go downhill. And I just try to walk down this hill. The issue with this is that each step of this method actually costs n computations, right? And if n is very, very large, say n is a billion, which is not uncommon, this is going to get really, really expensive. And so, OK, so what's a natural way around this? Well, let's just add some noise. So I'm going to switch to now a stochastic gradient method. Now, instead of actually computing things accurately, I'm just going to do them randomly. So now what I'm going to do at every iteration is I'm going to draw a random x from my data, whatever that distribution is. And I'm going to compute a gradient locally, just for that particular x and my current parameters. And then I'm going to take an update in what I believe to be the downhill direction, which may be totally wrong. But the idea is that there's more noise in this, but eventually it sort of settles down into the bottom of my function. We eventually walk downhill. And now the nice thing is that each step is actually only one computation. So this is going to be much, much cheaper. If we look on the left, this is 7 steps, but it's 7 n computations. The one on the right is doing 40. And if n is a billion, 7 times n is much, much larger than, say, 40. All right. So this is our picture. And now we can ask, so here's our algorithm. We're going to do, we care about using as few gradient evaluations as possible. Let's do this randomized stochastic gradient procedure. Is this efficient? Well, sometimes. And sort of this was originally proposed by Robbins and Monroe in the 50s and built upon by others. And notice that in some situations, this actually is an optimal scheme. This will get us the right answers, sort of, and in our computational model be good. But it turns out that for a wide variety of problems, as soon as we have data where the features are somehow high variance, or say sparse, like I said, we have these sparse data problems now in, say, text applications, this method is actually provably suboptimal. And if we're in a d-dimensional problem, sometimes we use a factor of d, the dimension, more computation than we actually have to. So we're using much more data, much more computation than we should. So where would we see problems like this? So let's, just as a simple example, let's consider a text classification problem. So I have, say, so here I'm showing this picture. This is a matrix, and each column in this matrix on the right side of the slides is a web page. And each row is a feature, meaning a word in the English language. A blue dot means that word appears on the web page. So we see, say if I look at just word indicators, a 1 if a word appears, a 0 otherwise, we have maybe 50,000 words. If we look at pairs of words, we can get up to about 3 million variables. But at most, say, in any given document, we have 1% of the words in pairs showing up. So this is super sparse. And it's also very heavy-tailed. Some features very common, some features very uncommon. So the word the appears about 1 of 20 times in the English language. And the word Frankenstein appears 1 in 500,000, right? So these are very, very different things, and sort of these standard stochastic approximation algorithms don't sort of use this information at all and can't deal with it. So if we look at the actual picture of what's going on here, of these standard methods, so if we think about our risk functional, we can look at the sort of topography of the function, and these curves represent sort of the level curves of our function, so it's growing up outside of the screen. And in directions where there's common features that show up a lot, we have somehow a lot of curvature information. The problem is easy. Very quickly we get information. In directions where things are very uncommon, we don't get very much information. It's going to take a lot of time to estimate these parameters. So can we do something a bit more second order, sort of recognize these geometries when we see them? If we could rescale everything to look like a nice sphere, well, then everything points downhill, life is easy, and we're good to go. But I've already told you all I can compute is sort of first-order gradient information. So what are we going to do differently? And what I propose is a method called addigrad, adaptive gradient, whatever you want to call it. And what it's going to do is essentially, at every iteration, so we usually just take a step downhill in some direction that we believe is the truth. But now I'm going to replace this step size eta here with this matrix. And what this matrix is it sums all of the gradients that I've observed up to the current point in time, and basically looks at the squares of the gradients I've observed, and then just constructs a diagonal matrix of those gradient squared terms. And I take a square root for certain stability reasons, and I rescale my gradients by that matrix. So this is efficient to compute, and I can compute it using only essentially gradient type information. All right? So this is my scheme. Simple adaptation so that I can rescale things in a nice way. But if you've seen like data whitening or something like this, then this is very similar to that, except we're doing this in this online setting where we don't need to know anything ahead of time about what data we're going to see. All right, so is this a reasonable thing to do? Does this work well? So we can let's start by looking at some empirical results. So this first one, we're going to just look at a text classification experiment. I said, we designed this algorithm for problems like this. So what I have here is documents from the Reuters newsfeed. And each document consists of about 2 million features, meaning words and pairs of words that might appear in a news article. And say only 4,000 of them are non-zero. I have maybe 800,000 documents. And what I'm showing on this plot is the accuracy of two standard methods, stochastic gradient and passive-aggressive, which is designed for these classification problems. And we're trying to classify documents as about economics, business, government, or medicine. And we see we have error rates of around, say, 6% to 10% for these different tasks. All right, and as soon as we switch to this adaptive method, we are using the same amount of computation for all of these guys. We're getting about a 25 to 50% improvement across the board on all of them. And also, if you look at these error bars, our error bars for these adaptive methods are sort of essentially an order of magnitude tighter. So we have a much, much less variability in the performance of these methods. All right? All right, so this is text data. But we kind of designed the algorithms for this. So let's try to understand what happens in a few other cases. So we can also look at image ranking applications. So here's our task. So we have a collection of about 15,000 nouns. And given a particular noun, we want to rank images. We have a collection of images. We want to rank them in order of the relevance for that noun. And so per noun, we have about 2 million observations in 10,000 dimensions. This is our representation. So the picture is somehow, we get a noun like dolphin. We want to rank all the dolphins ahead of all the pictures of, say, space. OK? And what I'm showing here is what's called precision at k. And so this is a measure of how many relevant results we return in the first, say, k results. So we see these are the two standard methods, passive-aggressive and stochastic gradient. And we see that passive-aggressive has about, I don't know, say 84% accuracy in the first position. So 84% of the time, it returns a relevant result first. And this decreases. So in the top three, we're getting about 80% accurate, and so on. When we use our adaptive method, just plug it in and run it for this ranking problem, we get about a 7 or 10% improvement across the board. And this is actually good enough that this is what's running under the hood, with minor variations in Google image search. So this has really actually had some practical impact here. All right, so for my last, I want to give one more result here. And I should say that I actually had nothing to do with generating this plot. So this is completely, it's almost independent of me. This was done by Jeff Dean and some colleagues at Google. And so this is a speech recognition experiment. So what I'm trying to do is I have a speech signal, and I want to identify phonemes in the signal. And the y-axis of this plot is the average phoneme accuracy, sort of per phoneme accuracy. And the x-axis here is the time it's taken to compute my estimated model, my phoneme classifier. We can see there's two algorithms here that are outperforming all the rest. There's a red algorithm and a green algorithm. And the red algorithm in about 30 hours has got 20 or 30 hours has gotten the same performance as the best performance of the green algorithm. And we can see sort of it's uniformly dominating it. So it's about 5 times faster to get to a fixed accuracy than the green algorithm. It also only uses 80 computers, whereas the green algorithm uses 800. That red algorithm is our adaptive gradient method that I was describing. It's actually an asynchronous variant of it that we've developed, so we can actually run this in parallel and without any type of locking or anything like that. This green algorithm is a synchronous BFGS method designed specifically for this speech recognition problem. And we're getting an order of magnitude improvement in time and cost. And this has actually been implemented and put into production in many systems at Google. And these problems are sort of essentially billions of features and tens of billions of observations for this particular problem. So, this is, we have some analysis, but this has actually made some real impact in industry. All right, so empirical results are fun, but let's also try to dig into the analysis and understand some of the theoretical results here. So here's my algorithm. I simply compute a gradient locally, and then compute this scaling matrix, which is number 2 up there, and then I'm going to update my parameters, but with this rescaled thing. Then we have a theorem which says that for any risk functional, any convex risk functional, our error rate looks like a sort of gap from the optimal parameter looks like something like 1 on n times this expectation. And this expectation trades off the size of this diagonal matrix A and then this other term involving gradients. But the exact form of this, don't worry about it too much. But the interesting thing is this is what I'll call an oracle inequality. So we're actually adaptive to this data. So even though we don't know ahead of time what we're going to see, we can actually cheat. And it's as though we're doing basically as well as if we knew ahead of time exactly what we would be seeing. So this is sort of an adaptive oracle type inequality. And we can also give sort of algorithm-independent lower bounds on these problems. So let me give a simple example. So suppose I have data x in d dimensions, say in -1, 0, and 1, and that the jth feature of x appears with some probability pj. And I want to just minimize linear functionals on the hypercube. So this is a stochastic linear program. So then we can prove a lower bound that says if all we use is n computations, n function and gradient computations, then our error rate, our gap sort of is at least 1 on root n times this sum of square roots of probability appearances. Now, the exact form of this isn't that important, but if we actually plug this into the bottom formula, we get this. And so if you look at this, essentially all quantities of interest are optimal. So we've really nailed down exactly, this is the right way to do this problem. Empirical results are good, and the theory we can actually give fundamental results that say this is unimprovable. And I should say, this is, I don't have a citation on the slide. This is based on joint work with Brendan McMahon, who's sitting 5 rows back up here. Anyway, and he's here all the time because he's at Google. Yeah, so let me just give some final remarks on computation. So this whole time we've been just trying to minimize this loss function. First sort of take home here, stochastic methods are good. We're going to use the data more efficiently, use computation more efficiently. But it's also good to do these adaptive things because we can actually adapt to geometry and give optimality guarantees for them, nice theoretical optimality guarantees. And I didn't state any results of this form, but it turns out in some d-dimensional problems, when we have sort of power law data, sometimes we can reduce computation actually almost exponentially in the dimension. So we can get dimension dependence that reduces from linear in the dimension to at most logarithmic. And the one take home, I guess, is that sort of these new schemes, these ideas actually arise from doing this minimax analysis of trying to understand, OK, how do we best take advantage of information I'm receiving under these types of constraints, and how can I pull out algorithms? So theoretical analysis leading to these practical impacts.
So can you comment on the diagonal approximation A and what impact it has on your problem?
Meaning if we used a full matrix, could we do better?
Yeah.
So we're making sort of here, we're doing this kind of diagonal scaling. And so the question is, what would happen if I used a full matrix to do the step size scaling rather than a diagonal matrix? In principle, we can get somewhat better theoretical results. In practice, that's just way too time intensive. And so
what's the gap in theory between introduce?
The question is, what's the gap in theory between the full matrix and the diagonal one? So we don't actually, I don't know that we don't have any sort of easily interpretable results on the gap right now. We have sort of formulas, and we haven't really nailed down exactly what they mean. So right now, it's almost just a theoretical exercise. But I don't know exactly what the dimension scaling is and things like that. We have a few examples where basically you can, again, get some kind of linear dependence on dimension reducing to logarithmic, but it's not completely clear. Yeah?
So this is for learning a linear function?
No.
Can you say anything about learning a nonlinear function?
Well, so this is for general convex optimization problems. So
what if the optimization is non-convex?
So what if the optimization is non-convex? Then certainly, well, our lower bounds still apply, but none of our upper bounds do. So you can't prove that non-convex optimization converges to anything other than a local thing. But yeah, what's that?
Maybe within some limits or given some properties or the size of the basin of attraction of the things like that.
Yeah, so we haven't done any analysis. I will say that this is a non-convex problem. So these things work for non-convex problems. We haven't spent a lot of time analyzing exactly how they work. And it's an interesting question, trying to understand, OK, how would they perform sort of locally? And yeah, we just don't know. But yeah, this is a non-convex problem. So at least in practice, they still seem to do reasonable things. Matthias, did you have a question?
I was similar enough.
Similar enough, OK. Yeah. All right. So done with computation. Let's take now jump up to communication and try to understand what happens if we view sort of communication as the resource or the constraint that we care about most. So why do we care about communication? We might have a distributed storage system. We might have, say, independent data collectors. Hospitals are collecting data on their patients, but they don't want to share information. There might be privacy reasons to avoid communication. If we put on our sort of engineering hats and just look into the actual structure of a processor, well, we have our sort of control units, but we have to communicate up a memory hierarchy, right? And every level up a memory hierarchy, we're getting orders of magnitude more expensive communication. And as soon as we have data distributed across many, say, machines or different agents or sensors, then we're getting even worse. And there's this National Academy of Sciences study on how we're going to keep improving our computing performance. And we don't know any way to do this except by doing things in parallel and distributed ways. So we need to address this. And communication is often one of the most expensive resources we have. So let's look at inter-machine or multiple agent types of communication schemes. And so my setting, admittedly, you should see this as sort of a first step here, is we have M machines or agents or sensors, and each of them has an independent sample from some distribution of size n. Okay, and then we have this sort of picture here where each of them is going to send some message zi to some central location where we're going to compute an estimator. All right, and we're not the first people to look at problems of communication and complexity and things like that, but we're trying to do this in this sort of statistical inferential framework. And so now the question is, okay, are there trade-offs, and what are they between communication and statistical risk? And how do we design procedures that best address them? Okay, so let's formulate this in our Minimax setting. So we have our central object of study is always just our expected loss, and we have our parameter space and family of distributions. We look at our usual Minimax risk, the gap in terms of between the performance of a method and what we could do if we knew the truth. But now we're going to look at the Minimax risk with bounded communication. So specifically, I'm going to say each of these messages z can be at most, say, b bits. And then we want to understand, under the constraint that we can only communicate b bits, what effect does this have on our learning procedures? If I restrict communication, what happens? Okay, so this is the same formula we've always had, except now it's communication constrained. This is our Minimax principle jumping up one more time. All right, so if I tell you, okay, let's use very little communication, what's a naive or sort of the first approach that one might take? Well, let's just try a divide and conquer procedure. So I have my local data, x1 through xn, on each of my m machines. And I'm just going to compute some local estimator, and I'll call it theta hat I. And this is going to be done independently of all the others. Then we're going to communicate all those little local estimators to the sender and aggregate them. So here's what we might hope our picture is. So these curves represent level curves of our risk. So being in the middle of all of them is good. And we might hope, maybe we're just randomly strewn around it so we can average and something good will happen. So the idea here is, since we're in these sort of noisy statistical problems, high accuracy isn't really necessary. Maybe a little bit of noise by doing it in this distributed way isn't going to hurt. And so the hope is that the picture looks like this, that we just get plunked right down in the middle by doing this aggregation. Turns out that actually for many problems, we can show that averaging in this way is actually statistically optimal. So essentially all you need to do is compute local solutions, average them, and you're going to essentially do at least very close to optimally. Okay, so let's just look at a quick empirical result here. So I haven't had advertisements in my talk yet, but this is a sort of joint computer science stat talk, so we should probably do some advertisements because the best brains in computer science should be working on advertising. Right? So we have 240 million observations here. I'm trying to solve a logistic regression model in about 750,000 dimensions. And what this plot shows is the x-axis is the number of splits of the data. So I have up to 128 data splits. The y-axis is our loss on some held out data. And what we see is, this looks like a big gap, but even with 128 splits, we're getting basically at most about a 1% degradation in the quality of our solutions. And so we're getting much, much faster estimation for this minor degradation in performance. And we can use this in many, many ways. So empirically, this looks actually kind of reasonable. And now the question is, OK, so I've said, statistically, this is a reasonable thing to do. Empirically, it looks good. Can we actually do better? Could we communicate even less? Maybe I can communicate much, much less than just this average. The answer is that no, it's not possible to do better. These simple averaging schemes actually are optimal communication-wise as well. So just to sort of, let's take the simplest estimation problem we can, which is to find the mean of some normal distribution. All right, so I have in d dimensions, I'm trying to estimate this parameter theta. Just trying to do, this is like the simplest learning problem we could have. Then if each of our machines has an independent sample of size n, then we can just compute all their averages if we have no communication constraints. And our error is basically going to look like the variance divided by the sample size, right? So we just compute an average, and this is what happens to averages when we look at their mean squared error. As soon as we put a communication constraint in here, what happens is basically I go from variance over sample size to this green quantity, d, divided by the minimum of b and d, where b is the number of bits I'm allowed to communicate, and d is the dimension. So I have this multiplying it. And so the consequence here is that, and I'm ignoring some log factors, which are maybe not totally sharp in our analysis, but basically the consequence here is that each machine needs to send about d bits to solve this estimation problem optimally. And we can't do any less than this. So yeah, so just wrapping up, basically for nice learning problems, things like classical sort of linear models and things like that, just averaging the local solutions is actually statistically optimal. And for mean estimation, regression, other sort of linear-ish problems, as soon as we're in d dimensions, we have to communicate at least d bits per machine. All right, so let's take our final step sort of away from these very local settings into sort of these broader sort of constraints at a very broad scale. And we're going to look at interactions with people as a constraint. So we want to maintain privacy in computing our estimators.
Sorry, just go back to your previous.
Which one?
The new thing. So the model of communication that you have here is communicate just at the end, an average,
yes.
Right? And you do this sequential work, which is 1 over n over m, I guess, in your notation, per machine. So you have n data points, you have m machines, you have to do at least n over m work, and then communicate at the very end.
Yeah.
And so if I wanted to get a better bound, my only recourse would be to increase the amount of work that I do at each machine, and not increase the amount of communication that I can do in this model.
In this model, yes.
So do you have any thoughts about what you could do if you could communicate more, but not compute more?
Yeah. So the question is, what happens if I could communicate more, but maybe I can't compute more? So maybe, this is, as I said, this is sort of a first step. There's a lot of work to be done here. Maybe we can actually communicate back up the chain instead of only sending messages one way, or things can interact. There are some scenarios where we can get substantially better performance. So like estimating a uniform distribution, it turns out communication can get exponentially smaller if we're allowed to communicate back up the chain. In sort of these, like estimating a normal mean, it's not clear. We have some results in sort of one dimension that say you can't get any better than this, but it's not clear what happens in higher dimensions. So yeah, this is totally open, and if anyone wants to chat with me, has any ideas, I'm happy to hear them. But yeah, future work, I think, is going to be a lot of fun here. Tons of things to do. All right, so privacy. So why would we want privacy? I mean, there are many reasons we might have privacy concerns, like I might want to keep my genomic data private. I might have some issues with sexual behavior, finances, substance abuse. But if we had access to these types of data, maybe this is offset by benefits. Biological bases of disease, better epidemiological control, forecasting, better treatment plans, foci, things like that. So the question is, what are are there fundamental trade-offs between maintaining privacy and statistical risk or statistical utility? And again, there are other folks who have asked questions like these, but trying to do this in this sort of statistical framework is a new thing here. And so to do this, we need a model of privacy. And the model of privacy we have is what's called local privacy. And this actually came out of work by Stan Warner in the 1960s, who was going door to door asking people survey questions and came up with a model called randomized response, if you've heard of that, where the idea is you ask someone a question, you let him or her flip a coin. If it's heads, he or she answers truthfully. Tails, he or she lies. So we're going to sort of work in a model that's essentially like this. And so the picture is the same as the communication case, except now our data x1 through xn is sort of private. And before the sort of procedure or statistician or whatever, get to see it, we have to make it private and turn into some z. And so the picture is there's some channel, which I'll call Q, which takes in the data X, and then it obfuscates it in some way, and out pops Z. Say we add a bunch of noise, something like that. And now so we have these individuals with private data, and then we try to construct an estimator based on only seeing the obfuscated views of the data. All right, so we need a definition of privacy, and what the definition we use, which sort of abstracts from this notion, is what's called the alpha differential privacy. And so what this says is that so Z is some now random variable, and the distribution of Z can't change very much based on where the initial data started, either X or X prime, whether the data is my data or, say, Carlos's data, what you see looks about the same. And so the intuition is somehow that given Z, every X is just as likely to have generated the Z as any other X, so you can't recover it. And there's sort of testing interpretations via Neyman Pearson and other ways to interpret this. OK, so this is our definition of privacy. And now we can do the same thing we've always been doing. And we're going to look at our Minimax principle and see what happens. So we look at this Minimax risk, best estimator, worst distribution. And we make just the usual tweak. We look at all possible private distributions under this notion of privacy that obfuscate the data. And we try to understand, OK, how does this affect our estimators? What is this Minimax risk when I've constrained my procedures to be private? So this is just the same thing we've been doing for this whole talk. All right, so I'm not going to get too deep into the theoretical results here, so let me give just a vignette. And suppose I have patients admitted to a hospital for substance abuse, and I want to estimate the prevalence of different substances in their system. So I might say I have alcohol, cocaine, heroin, marijuana, LSD, or amphetamines that I care about, and I have some true proportions in the population that I want to learn. And you guys might object. It's impossible to actually overdose on marijuana, but that's purely academic knowledge, just so everybody knows. Anyway, moving on. So we want to estimate these population proportions. And so maybe we ask, OK, what's the optimal way to do this? Is there an optimal scheme for this? So our first strategy might be to say, OK, somebody comes in. These are the true drugs in his or her system. Let's just add a bunch of noise. OK, so this is our first idea. Just add a bunch of independent noise, and that will make things obfuscated. So we might say take data from a Laplace distribution and just add it in. It turns out that anytime we do this additive noise, the magnitude is much too large. It's actually provably suboptimal. This gives us the wrong results. So what's the right scheme? So the optimal mechanism here, or one optimal scheme under our metric, is basically an analog of this coin flipping thing I said. So we pick a random vector v, uniform in 0, 1 to the d. And then we look at v and 1 minus v. And we're going to and I, the guy who's trying to collect data, will see one of these two vectors. And what we're going to do is we're going to flip a coin. And if that coin is heads, then I choose the closer of v and 1 minus v to x. And if it's tails, I choose the one that's farther away. So basically, I just hand you a coin and two vectors. You flip the coin. The coin is heads. You answer closer to your truthful signal. And if it's tails, the further one. And we do this for every patient in our study. And then at the end, we're going to compute the sample average and debias. All right. So this is the optimal scheme. Is this essentially this kind of coin flipping thing? All right. So does this matter? Maybe this doesn't matter at all, and we'd be just fine just adding noise. So right now, I actually have a data set of people visiting the emergency room, and I have about 65,000 patients. And what I'm showing here is my maximal error in estimating the true population mean. So if we do additive noise, this is the error versus sample size with a 95% confidence interval, we get an error of about 0.1 in the maximal error of about 0.1. If we had no privacy, meaning we could actually compute our estimators like we want, we get an error of about, say, 0.001. All right, so this is no privacy. But this optimal scheme is equally private, and we're getting about an order of magnitude improvement over the truth. And so this is the optimal scheme's performance versus sample size on this data that we've collected. OK, so this actually, this makes a difference. It's good to be optimal. All right, so I'll just give one theoretical result here. So if we abstract a little bit away from this problem, let's say I just want to estimate the mean of a distribution where the distribution has data in -1, 1. Right, and I'm going to estimate want to get my maximal error as small as possible. And we can give the following theoretical result. So if we have no constraints on privacy, meaning I'm actually allowed to see the data, then my error rate looks like something in my maximal error in L infinity norm, looks like something like log d over n. So d is the dimension here. So even in high dimensions, we can do this estimation problem, this learning. And this is just we average the data, and that's our estimator. Turns out with privacy, as soon as I have this alpha quantity of privacy, I actually go from log d on n to d times log d on n. So I'm actually getting a much, much worse dependence on dimension. And so effectively, whatever our sample size was, n data points, now we have n alpha squared divided by the dimension. So we're losing something by this privacy notion. All right. So final remarks. Yeah.
But why is the optimal optimal?
Why is the optimal optimal?
Right.
Because it achieves this.
I know, but why?
But why intuitively?
Yeah.
So I mean, if you look at this.
Why is your scheme optimal, right?
Yeah. I mean, well, okay, so I'll say a few things, and we'll see if it satisfies the question. So, sorry, the question was, why is the scheme I proposed, this kind of coin flipping thing, optimal? So if we look at this, effectively, we've lost sort of d dimensions. And what this optimal scheme is saying in some kind of information-theoretic sense is basically I'm giving you a code book of 2 words that you can use to communicate. So you can communicate 1 bit to me, essentially. And this is what our Minimax rate sort of is doing. So you can communicate 1 bit to me under this privacy constraint. And the question is, how do I best distinguish sort of one signal from another? And the way we can do that is via this coin flip to say you're closer to this extreme point or this other extreme point. And so if we're only communicating 1 bit of a d-dimensional signal, this is why we lose sort of d dimensions, essentially. Sort of that's kind of some of the intuition floating around here.
That's for your upper bound, but not for your lower bound, right?
Yeah.
There could be another schema that doesn't throw away as much or something.
Yeah, so there could be another schema, but the lower bound says that that is actually optimal. So we actually have to throw away that much information.
And would you have the same behavior if it were not max norm?
Yes, this behavior is sort of norm independent, but
I see.
This one makes clear exactly where the dimensions come in. So we go from logarithmic to linear in the dimension. Yeah.
Vector v, is that the same for the population, or are you independently choosing one and recording it?
Yeah, the question is that random vector v, does it change as you go through your data? So let's go back to the scheme. Is it the same for all the data, or is it different for each person? And the answer is it's different for each person. So each person gets a different random vector v, or a new random vector v, yeah.
So that's recorded as part of the data. The 1 bit of information you got plus what it was
plus which vector v it was, yes. Yeah, so it's 1 bit, which is, and what the sort of code book, or whatever you want to call it, was. Yeah. All right. So let me wrap up this section on privacy now, and just say that sort of we have a bunch of additional examples we can work through. Yeah.
I'm guessing you don't store the bit. You only store the vector. Because if you store the bit, you tell them which vector they have.
Oh, sorry, yes. We store exactly the vector, which is one of the 2 vectors we could have sent. Thomas, yeah.
Connected question to that. So this also, the privacy guarantees presume nobody is asking the same questions and keeping track of your responses, right?
So the question was, the privacy guarantees presume no one is asking the same questions.
Asking you the same questions, so you're not going into hospital multiple times, and there's no possibility of somebody doing
Right, so I can't go to, right, so the question is, can I ask the same person multiple questions? And the answer is, in this model, no. I can't, I mean, as long as sort of the sum total of those questions satisfy our privacy definition, that's fine. But yeah, I can't keep asking you the same question, because then eventually I'd figure out your information. Okay, so just wrapping this up, we have a bunch of additional examples. Fixed design regression, convex risk minimization, estimation of multinomials, non-parametric density estimation. And essentially in all these problems, we almost always see an effective sample size reduction of at least n going to n alpha squared, where alpha is that privacy parameter. But in d dimensions, or some place where there's some analog of dimension, we lose something that's essentially dimension dependent in these problems. And I'm happy to go through the reasons for that sort of offline if anyone has further questions. All right, but just to, again, I think that the key thing to take home here is, there's this minimax analysis that happens, but it actually allows us to identify new optimal schemes. Something you might not think was optimal, now we're actually able to sort of pull it out and identify what the optimal way to solve these problems is. basically what I've been trying to do is bring in these constraints in Minimax analysis. And for all of these sort of lower bounds are actually central to our analysis, is figuring out what the lower bounds are on these estimation and learning problems. And the way we do this is by actually constructing a testing problem. We want to solve a test to figure out, we have some state of the world, which I indicate by V, and we want to construct a test that identifies the state of the world from what we can observe. But we only can observe some vector Z. So X is the true data, but it turns into something else because we have a constraint, like that we're doing optimization, so we only see a function value, say, or we're doing communication, so we only see a few bits, or we have some private signal. And then we developed a bunch of information-theoretic inequalities to relate the actual amount of information in what we can see, sort of this vector Z, to what would have originally been there in the true problem. So we have some original data, but we're losing it, and we explicitly can quantify exactly how we lose information by our constraints. And then we apply sort of standard and some new information-theoretic techniques to give these lower bounds. And this understanding leads to new optimal schemes. So wrapping up, this whole talk, I've been trying to use this minimax risk as this principle, where we look at sort of what's the sort of worst case risk for the procedure we're developing under the constraint that my procedures have some resource limits, say, because they have to use low communication, computation, or are private. We developed a bunch of techniques for lower bounding our risk with these constraints, but we've also given a bunch of new provably optimal schemes that have really nice practical performance. And the hope, of course, is that this is just the tip of the iceberg, right? I think the model of computation that we've put forward is certainly a fairly restrictive model of computation. So we can imagine many, many other models of computation. We might say try to understand power constraints on estimators or different modes of communication, things like that. We might try to understand, say, in ranking problems like web search, we can only get very partial views of people's preferences. That could be a constraint. And try to understand, OK, how do we best solve inferential problems under these things? Anyway, I think this is just a really exciting area, trying to understand exactly how we bring in kind of computational and practical considerations into the design of our estimators. And thanks for your attention. I'm happy to take questions.
Thank you. We have time for a couple questions. Yeah.
Presumably there are many procedures that will also achieve the minimax rate. Minimax isn't usually achieved uniquely at something. So it seems like, well, sort of A, are there other things you think might also be minimax? And then B, to distinguish among minimax procedures, it seems that you want to use information about where your truth actually lies. So for example, in a lot of your problems, it seems likely that you're going to have some sparse solution as the truth. And so to evaluate procedures, would you consider evaluating them in those parts of the parameter space rather than just the minimax?
So the question was, and correct me if I miss anything. So the first question was, OK, Minimax essentially is it's a somewhat pessimistic hammer, and oftentimes many procedures are basically getting the Minimax rate. So are there other optimal procedures? Maybe. That's the first question, right? And the second question is, since it's such a sort of kind of gross hammer, is there something a little more precise we can use maybe to characterize more local notions of performance? If we knew something about our problems. The answer to the first one is I'm perfectly willing to believe there are other optimal schemes. These are at least these three examples. These are the three we came up with. We feel like they're fairly natural. In the privacy case, we're close to guaranteeing uniqueness, but we don't exactly know how to do it. The other ones, I'm not sure, but we could certainly. It'd be interesting to understand. In terms of sort of more local notions of complexity here, a lot. Yeah. So the question, so many times we could actually have, say, like an adaptive procedure that, say, for subsets of the parameter space P is still optimal for those subsets. And with these constraints, I don't exactly know how to develop adaptive procedures. I think that's a great question that we'd like to understand more. And at a grad, that first bit was trying to get something close to adaptivity, because it was adapting to the actual problem instances you had, and that's what made it optimal. But sort of in the other situations, the communication and the privacy ones, we're a lot farther away from dealing with that.
Other questions?
So nature is usually not hostile, right? Maybe in the privacy case, but in general, right? Minimax is, why use Minimax as the objective?
So the claim is that nature is usually not hostile. So why use Minimax as the objective? I think there are a few answers for that. One is that we need some way to compare the performance of procedures. We need something that is definitely going to give us an ordering. So Minimax is one way to do it, and it's a way to get a handle on some of these issues. So that's one thing. Another thing is, it turns out, actually, practically speaking, oftentimes a Minimax, in many cases, a Minimax procedure does pretty well. As we saw in sort of the first part of the talk, and in the communication cases, these are actually doing reasonably well in practice. So something's happening in our analysis because, it's coming. It may be Minimax optimal, but we also have other kinds of guarantees like adaptivity, like Peter's question, and things like that. So, if you get lucky, maybe you can actually solve things much, much more easily. But I think what you want to do is have like a Minimax a procedure that's guaranteed to be Minimax in the worst case and does better if there's some nice structure to your problem. So developing procedures like that are going to be very interesting. And
the average case, right? Because in many cases, that's all you care about.
Well, what are we taking an average over? I guess that becomes the question, right?
Yeah, sure.
So in many of these cases, our lower bounds actually, we lower bound an average case complexity. So the lower bounds are often not actually a max. There's an average over possible states of the world, and we're still getting hit by this. But we just somehow we need to have a principle, and understanding exactly what that is it's almost a philosophical question, really. But there's still randomness here. There's averaging over. Shoot, this thing doesn't work again. There's averaging over the data happening. So there's already some averaging going on. It's just a question of exactly how much averaging we like. And I get to choose that set script P. If I feel like being non-adversarial, maybe I make it a nice set, right? But it's up to me, because I'm the one developing the algorithms.
You could have a distribution over it.
What's that?
You could have a distribution over it.
Yeah, if I have some beliefs, I may as well just use them. I'll put in anything I can to make my life better, and then try to understand it. So we could certainly do that. We get to do that. So.
All right. Let's end here and thank the speaker again.